All right, welcome back. We are Game 2005, that's Game Physics, in the fall 2021 semester at George Brown, and it is week 2, part 1 of our broadcast. Before we begin, I'm just going to get the link to our YouTube video for those people who need additional support. Again, I'm going to put that up on under the week 2 content area for those people who need to watch. And I'm just going to add in a YouTube video link for you guys. You should be able to do this right now for those people who need to watch the video. Okay, there you go. All right, so these videos, like I've said in the past, cover a couple things. They cover the schedule for us for each individual semester. So that's the one thing. So even though the content is very similar to previous semesters, like there's going to be very a lot of similarities, if almost identical stuff sometimes. What we will be having in other cases is the due dates, the time frames, and all that kind of stuff. It varies according to the semester we're doing this thing in, but for the most part, it's the same. So this week, we're releasing assignment 1. It's going to be due on week 4. The details for assignment 1 have been posted for you up on Blackboard. All right, so if you look at assignment 1 will allow you to work in groups or on your own if you want to. Remember what I've asked you to do with assignment 1, and it requires you to also make a short video. I'm going to start with assignment 1 requirements right now. Very quickly, talk about assignment 1 and what you're going to have to kind of put together. It's worth 10% of your final grade. It's due Friday, October 1st, 2021 at midnight. Again, there are a couple of sections, and I'm not going to go through the details of the assignment. I think you can do that very nicely in lab. But for the most part, it's like this. Part 1 is a physics problem that you need to solve. And it talks about this thermal detonator, Star Wars, a Wookiee is going to throw it, and so on. And this is the first part. I think this is the easy part to do, where you kind of talk about things like the distance the stormtroopers are away, 485 meters away. As an example, what is the correct angle for the Wookiee to throw the thermal detonator? We'll go into how to do that in some of that stuff at the stormtroopers. What is the maximum distance the thermal detonator could travel based on the Wookiee's ability to throw it, and include some kind of short document or report that includes a diagram that illustrates the problem in your solution. Ensure you include appropriate labels and show your work. Some people forget to do this and they lose 10 marks. Please don't forget, short document is important. Show your work, that's super important in order for you to calculate those things. The second part is a physics simulation using the SDL framework that we've given you. We've given you an assignment framework. And there are some requirements. Please read carefully about what I'm looking for from this assignment. Again, it's fairly straightforward. All I care about is, kind of demonstrating your assignment with the the SDL framework. And then the third part, which is something you're gonna have to do, is you should include a current image of you and your partners in a single slide. It's not separate. It's going to be like the first scene of your video should include a slide of you and your partners that basically talk about, hi, my name is Tom, and this is my partner Joss, and we are working on assignment 1 for Game Physics, Game 2005 in the fall 2021 semester, and let me demonstrate my assignment. Here it is. And so you're going to demonstrate your assignment and make sure I can hear you and see your screen and so on. There is a version control component for this one where you have to put it up on GitHub, and your repository should be well structured, and it should include commits that demonstrate the project being updated at different stages of development. If you just put up on GitHub as a backup, you lose marks. And your project will not be accepted without your video demo, so it's kind of a mandatory submission. This is the breakdown of your marks. Your problem, physics problem is 30. Physics simulation in user interface in SDL is 20. Your physics simulation functionality is 35. So 55% of your grade is your demo in the app. Version control is 5. Video presentation is 10 for a total of 100%. And again, the requirements that you submit are a Word or PDF document to show you the work for your physics problem in your diagram, some kind of name and student ID for each member at the top of your document. It's very important. A link to your working GitHub repository for your simulation, a zip archive, not a RAR archive, of your your project on Blackboard, and a link to your video demonstration. Or worst case scenario, maybe a link to, if it's on YouTube, it could be on Google Drive or OneDrive or whatever. Hopefully I won't have to download anything. This thing is worth 10% of your final grade. Again, it's due 2 weeks from now. All right, so questions around this before we move on for the day. Do we need to make our GitHub repo private and then add you in, or we just put it in public? Private would be best, and you should include myself and Joss. I will put some notes, an announcement on Blackboard that indicates my email address that I prefer. And if Joss likes his email address, if it's going to be private for him, his email address for the labs. I'm not sure if he wants his labs private or public, but definitely for the assignments, they should all be private repositories that are shared between you and your partners. Okay, so hopefully that's good enough. Okay, so that is assignment number 1 in some level of detail. Again, please go through it step by step, go through the details. You've seen assignments from me before. This is not the first time for most of you. So I think that you can work in pairs, Samantha, or up to another person, up to 3 people I would allow. And the reason why I'm saying up to 3 is sometimes, you have additional work to do, especially when it comes to graphic assets and so on. One thing I'd like you to do for these assignments is make sure that everybody has a job to do. If you're going to employ 3 people, you better all be awesome in terms of what you're producing. But you can also do this thing alone if you're interested in doing that. Okay, so that is something that we're doing this semester, and again, do 2 short weeks from now on week 4, and then you'll get your second one, which will be due by week 6. Any questions around this before we move on? All right, no questions. Let's get going. So, this is section 2. Last week, we kind of did a background on geometry. We talked about triangles, a little bit. We talked about how to solve a triangle and how triangles are a key in terms of understanding, structures on the screen. So in terms of, if I want to find an angle, as an example, how do I do that based on if I have a triangle? And triangles are useful because that's one way we can use, one thing we can use, a tool we can use to solve physics problems. So today is the first day we're actually doing real physics, specifically for game dev. All right, so is it physics that we would use in the real world? We can use some of this. It comes from the real world, but it's really geared towards you as a game developer and game programmer. So the first thing we're going to be talking about is a new term called kinematics. You guys should know about that a little bit from AI. We talked a little bit about kinematics, right? Kinematic motion as an example. And it really describes motion where we're ignoring external agents, that might have caused or modified that motion. So we're not really taking into account external agents for now, right? And when we think about motion in one dimension, we're really thinking about motion along a straight line. Okay, so how does motion work across a straight line? And really, when we think about what it means, motion represents this continual change in an object position, right? When I'm thinking about continual change or a continuous anything, if something is continuous, I'm thinking about calculus. And one of the things that we had in this course in prior semesters was we had a calculus component. And luckily for you guys, we don't have that this semester because I find that we haven't used calculus in programming for a while. Is it useful to check your work and to make sure that you're calculating things properly outside of programming, outside of code? Absolutely. Will you get calculus this semester? No, you won't. So there's different kinds of motion that we've talked about before: translational, rotational, and vibrational. For the most part, we won't be doing a lot of vibrational stuff, although I'll be talking about it. For example, the back and forth motion of a pendulum or some kind of spring action can also be vibrational. And translation obviously is car moving across the highway. Rotational is, the Earth spinning around its axis, and so on. When we think about physics, what we're going to be using this semester is the idea of a particle model. So even if the model is a spaceship, a starship, some kind of actor that you're going to have on the screen, we're going to be simplifying the idea behind them, and we're going to think about anything that you have in your game or in your assignment framework as a particle. And this is going to really simplify the way we move things. So things like soft body physics and those kind of things is something that you may have to explore in another course. We're thinking about rigid bodies where the center of mass is pretty, symmetrical at the most part. And the assumption is that it's in the dead center of your sprite from a 2D perspective. Okay. Position. When it comes to the object's position, a starting position, and again, I'm going to go fairly quickly today because we have 79 slides that I want to cover, and we have very little time. The object's position is a location with respect to a reference point, some kind of reference point. Usually it's like the origin, which is 0, 0. In this case, we can use a number line. You can see that the cars at positions A and B are to the right of the number line. And cars at position F and E are to the left of the number line. They're, based on the coordinate system that you've accepted, okay? So we're really only interested in cars' translational motion, and we model everything as a particle, okay? So when we also look at stuff, and this is a very interesting and useful thing to look at, and Joss will say a lot about this potentially because he loves these position time graphs as well as I do. Position time graph really describes motion over time. So what we have is an amount of displacement here in this on the y-axis, and on the x-axis it really describes the time. So what is the distance we've moved over time? So you can clearly see what this says. At time 0, we start at a distance away from the origin at about 30 meters. Okay, notice that is the case, right? And then as we move to time 10, so 10 seconds, it takes us 10 seconds to move from, 30 meters from the origin to approximately something like maybe 55 meters or something like that. It's just slightly above the 50 marks. I would say 55 meters away approximately from the origin. At time t is 10 seconds, right? And then as we move into 20 seconds, you can see that you actually do a little bit of backward motion. So we're moving back towards the origin just under 40 meters. So let's say around 38 meters or something like that. It looks like at time is equal to 20 seconds. And finally, at time is equal to 30 seconds, you are at the origin again. So back to where you started, or the reference point, if you will. And then you can see that you're behind the origin in time 40 and time 50, further back. Okay, so that's how it works. So this describes motion over time. It doesn't necessarily describe forward motion. It can describe both, all right? So it's interesting the way this can work. So we use a data table, and we've seen a data table last week when we talked about how to plot a graph manually. If I was going to plot a graph manually, I used Desmos to help us out to make sure that we kind of understand how to plot X and Y coordinates. And you can see here, the position of the car at various times can be displayed or expressed in a graph, and this is what you're seeing here. Okay. There's different representations. A lot of times when we get a problem, and I always talked about this last week, we started talking about this already, is I want to start graphing it out or making a picture, some kind of representation of the problem. And what happens for us is it's an excellent strategy. We start making a picture, trying to understand what the problem is telling us and how to solve, what tools we can use to solve every different problem. So that's how you start off. Again, there's different alternative representations. For example, some people might really like to use some kind of pictorial representation, or a graphical representation, or a tabular, some kind of table representation. And the goal is often to change that, whatever it is, the representation we're using, and convert it into mathematics so that way we can understand in the language of math what is happening in the physics simulation, right? So that's what we're doing. Let's talk about displacement a little bit. So displacement really is defined as the change in position during some time interval. Okay, this is important. So we can think about the change in something as a delta, right? So a lot of times we see this Greek letter delta, and it's in front of something like an x. Delta x means the change in the x value. So delta x is equal to, and this, you might see these small little marks here. Again, this is a reminder of what these units mean, right? But I want to kind of zoom in here. So where delta x is equal the position of x final minus the position of x initial. So the difference in position, right, is your change in x, right? That's the change in x. So the units of measurement for this particular thing is meters, right? How many meters? Typically, we talk about in meters. Delta x can be positive or negative. And I want to indicate, then people get a little bit confused, that distance and displacement are the same thing, but actually they're not, okay? Let's think about what that is. So here's distance, right? So assume a player moves from one end of the court to another, as an example, and then back again. The distance is twice the length of the court, right? Because distance is always positive. I've traveled some length. I've moved, I've displaced, but my displacement though is 0. Why? X final, which is the final position, is equal to the initial position. If the final position and the initial position are the same, the total displacement we can say is 0 units, or 0 meters in this case. And so that concept is important. So how much have I displaced myself from the origin? That's what I'm talking about here. And you could have a negative displacement if I'm behind the origin. Right. Vectors. We can't do anything without vectors, and we've seen that already when we did AI. I would say vectors and scalar quantities are kind of the tools we use in game programming to really understand not just the distance but the magnitude when it comes to direction, when we're moving, when we have motion happen, and especially specifically with physics simulated motion. Okay, we use vectors for the most part. So again, both magnitude and direction. Scalars, however, all we care about is the magnitude only. They're just a single value. All right, so scalars and vectors. So how this works is, here's something else we want to talk about, the average velocity. When we think about describing the average velocity of an object, right? When we think about velocity in general, velocity is related to displacement in some ways, right? So we can see the displacement formula right here, right? X final minus X initial, right? So no displacement, no velocity. That's important to understand, right? So when we say something like the delta X, the change in X, the displacement of X over the change in time. So change in X over the change in time is your average velocity across the X-axis with respect to X, which is what this Vx average means. So your average velocity with respect to X. And then the X indicates the motion along a specific axis, in this case, the X-axis. The dimensions are usually length and time, where length is in meters and time is in seconds. So again, we have meters per second as the units, the proper units for velocity. When you make your assignment 1, please indicate the appropriate units or else you'll lose marks, right? So it's also the slope of the line in the position time graph. So that's one thing we should know as well. That's what the average velocity is, okay? How about average speed? Average speed is different than velocity, right? Because we don't care about displacement, we care about distance. So the total distance over the total time is the average speed. So normally we also have V represent speed. Sometimes V is velocity, sometimes V is speed. But the difference between velocity and speed is velocity is a vector, speed is a scalar. Okay, so this is the important difference between the two, right? So again, speed, no direction required. We just need to know the total distance over the total time. That's the most important thing. And it's usually in a positive number. We don't have negative distance. There is no such thing as negative distance. It's only positive distance. Either you moved or you didn't move. Okay. So again, one thing to note is the average speed is not the magnitude of the average velocity, right? For example, here, a runner ends at her starting point. So starts running, comes back. Her displacement might be 0, but her velocity, right, is 0 because there's no displacement. Because remember, the displacement function, going back a couple slides, right here, x final minus x initial, is required to calculate your average velocity. So therefore, the displacement is 0 because her velocity is 0. However, the distance traveled is not 0, so the speed is not 0 because you've traveled a certain distance over time. Okay. Giuliano says, so the average velocity in the last example was 0. Yes, because if you go to the on the court as an example over here, and you go from here to here and then back, because there's 0 displacement, there's 0 velocity. Why? It's a vector, right? Imagine you're adding two vectors together. Look at those vector lines, the green vector and the blue vector, right? You've adding those two together, one cancels out the other one, and you end up with 0. Okay, you're back at the origin, in other words. And so that's important. How about the instantaneous velocity? And this is where calculus would be able to help us out, where we want to say the limit of the average velocity as the time interval becomes infinitely shorter and shorter and shorter, and as it approaches 0. As we approach 0, can we calculate the instantaneous velocity at a specific point in time, right? So we can do that. And what we do is we use these tangent lines, right? As an example, tangent to the curve. So we start doing lines tangent to the curve, and we can kind of think about these secant lines right here. As they're tangent to the curve, we can, at the point where they're perpendicular, so the angle of the line is perpendicular to the curve, that is the instantaneous velocity, we can say. And again, we can figure that out with calculus. But what we want to try and do here is we want to be able to express any of these areas here as like, for example, this B, that B, this B, and this B. These are all areas that are going to be, we can see that there's a distance or a direction from the origin, right? But it's also, if we were going to use I'm just going to annotate this for a second using Zoom. So bear with me. So if we're going to make some kind of, if we're going to draw a line, right, that was tangential to the curve, right? So again, we would kind of draw it like this. You can see that there's several lines we would draw, one for each point. I'm just trying to draw this as best as I can, tangential to the curve. And you can see that, oops, that's wrong. You can see that as we go, we want to make it as, and it looks like a bit of a spiral graph. But the idea is that each of these tangent lines, where it touches the curve, that is where the instantaneous velocity is, all right? And again, it's related to, it's got to be perpendicular or at 90-degree angles to the curve itself, okay? So that's how we would find the instantaneous velocity. And again, we would use a tool like calculus to help us with that. Okay. Let's continue. So note about slope. Slope of a graph, and when it comes to physical data, represents the ratio of the change in the quantity represented. So the rate of change of something. When I say rate of change, anytime in my mind when I'm thinking rate of change, I'm thinking calculus, okay, all the time. We can also represent the rate of change as by using limits, right? So we can kind of read it like this. The velocity or the instantaneous velocity across the x-axis, and you can see that there's a lim here. Lim means the limit, right? The limit as we approach time, where time approaches 0, right? As an example. So the limit as the change in time approaches 0. For the change in x over the change in time is equal to delta dx over dt. And this is where we start thinking about, calculus. We can kind of derive, the instantaneous velocity a lot of times from the position graph, right? And that's what happens. Our first, if you will, derivative if we were going to talk about derivatives in calculus, and for those of you who did calculus in high school, you may have forgotten it, like a long, well-forgotten dream. Or a nightmare. You've forgotten about calculus because you don't like it. As an example, well, when we come to derivative, or the first derivative, as an example, is usually from position, we can infer or derive velocity. From velocity, we can infer and derive acceleration. And we can go back using integration. And we'll talk about that, over, the next course of time. So when we say the instantaneous speed, then it's the magnitude of the instantaneous velocity. So that's a little different. So this is where speed and velocity kind of have some kind of association, but instantaneous speed doesn't have a direction, whereas instantaneous velocity does. It's a vector pointing in a specific direction, okay, away from the origin. So when it comes to vocabulary, when we think about vocabulary, and you may have already known this stuff because we've been working with vectors for a while, velocity and speed will indicate instantaneous values, and the average will be used when the average velocity or the average speed is indicated, okay? So one thing we're going to be talking about this semester is a way of analyzing problems. So I'm going to start analyzing problems, and there's different models we can use to analyze the problems. So again, an analysis model is some kind of description of the behavior of some physical entity or the interaction between the entity and the environment. We can also call the environment the system, okay? How the entity, the object, if you will, interacts with your game environment or game area, okay? Game space is another way of thinking about it. All right, and based on 4 different models that they use from the book, we have the particle model, the system model, and the rigid body or rigid object model. And we also have the wave model. We're not going to use the wave model because the wave model is a little bit out of scope with what we're doing in this semester. If we were going to strive, if our physics was about light, and sound, then certainly we can use the wave, particle and wave model together. But here, all we care about is the particle model because, and for waves, the only thing we might use something like a wave model is when it comes to any kind of vibrational effects. Again, things like oscillations with a pendulum or some kind of oscillations with a spring. It kind of produces a wave effect. Okay, so again, when it comes to a problem approach, we identify the analysis model we're going to use, and then the model tells us which types of equations we can apply. Okay, that's how it works typically. Okay, so here's a model. And the model that we're going to use right now, we're going to talk about is a particle under constant velocity. So what if we have a situation like that? Well, if you look at the particle here, a great way of looking at this is the vector. If you actually identify or look at the red line here with the arrow, you can see that the vectors are equally spaced and equally sized. That's a good indicator that there's a constant velocity being applied. And the reason why we're saying constant velocity, because it's going in the same direction, right? And the intervals, right? Think about this, if each interval for us, because we care about frames, but the intervals here would be in time steps, right? For each time step, you can see that the interval is identical, right? Constant velocity is a good way of looking at this. So again, when we describe this in math, we say, velocity x is equal to the velocity average in this case, right? Where the mathematical representation of the situation is this equation, where we say, remember, just like before, x final minus x initial, that's the displacement, over delta time, which is the change in time, right? Or when we massage the equation and solve for x final, we can say that the final position is equal to the initial position plus the velocity across the x-axis multiplied by the change in time, or x initial plus vx, v with respect to x, right, times delta time. All right, so again, common practice is to let time initial equal to 0. And so when we start thinking about time initial in the equation, then the equation gets simplified to x final is equal to x initial plus vxt for constant velocity across the x-axis. So this is your first equation, okay? And we're going to see, you're going to be given today a set of kinematic equations that you can use to solve motion in one direction, okay? How about what does it look like on a graph? As an example, again, if you look at x as displacement and t over time, you can see what is happening here. As time increases in this, when we look at this particular graph, there's a linear correlation between time increasing and displacement across the x-axis. So this is what a particle under constant velocity looks like, because it's just a linear graph, right? If it was accelerating, then the graph would be a curve, right? But it's not accelerating. It's staying at the same speed all the time. When it comes to a particle under constant speed, okay, so we talked about a particle under constant velocity. Here, we're talking about a particle under constant speed. Remember that speed is a scalar, velocity is a vector. So here, what we have is a particle under constant velocity moves with the constant speed along a straight line, right? But a particle can also move with constant speed along a curved path. So when we think about this, as an example, you can see that here is a curved path, right? And you can see that the distance traveled is pretty good because we keep on changing our velocity vector, right? The velocity vector, although it's under constant velocity, is going in different directions, as an example. And yet, we don't really care about the curve so much at the end. When we describe velocity, what we really care about is the displacement away from the origin. And so what we can do is, let me just choose another color here, is we can map a line that goes between the origin, the place where the particle started moving, and the last position in our curve. That is the total displacement. And so therefore, if this is the total displacement, we can produce an average based on the total displacement from x final minus x initial. It gives us the total displacement over time, which gives us the average velocity. So you see there's a relation, even though the distance traveled along the curve, as you can see, is much greater than the velocity, right? The magnitude of the velocity, the average velocity. Okay, any questions so far around the difference between velocity and speed? So again, constant speed, you might have a constant speed as you're tracking along the curve, right? Constant speed, right? But when it comes to velocity, we don't care about you going around a curve, right? We don't care about that. We just care about the displacement away from the origin. So here's the origin, here's the final position. We just care about this line, right? So we can say that the final or the average velocity is kind of in this direction, isn't it? Right? This is our velocity vector at the end of the day, right? However, it's not describing, the curve in any way, right? We could have a particle move like this in our game, right? But when we describe the final velocity or the average velocity of that particle, we're not really describing each segment. For example, we have a segment, let's say from here to here, right? So let's say this is a time segment. And in this time segment, we have a velocity vector that goes up. And then we have some other time segment that goes this way, as an example. And I'm just putting it across, kind of something that makes sense. Let me just undo. Maybe what I can do is, kind of map it to each of the particles as close as possible with my eye. So these are the intervals. Again, I'm just using the annotations as an example. So across each of the intervals, let's suppose these are all seconds, right? As an example, there you can see that the intervals are fairly uniform based on my simple, silly drawing, right? So let's suppose these are all seconds. So you can see that every second, the velocity vector is changing, right? But at the end of the day, All we care about when we talk about average velocity is this, whereas average speed is the same, right? All right, so, and we don't care about direction, when it comes to speed. All we care about is the total distance traveled over the total time interval. The green line here, this line here, represents the displacement. Absolutely. Yeah. And the magnitude, right, represents the average velocity or the total velocity. All right, so, and then we take that total velocity over the time interval and we get the average velocity. Okay, let's move on and let's get rid of that little drawing. So again, I think, the great thing about thinking about these kinds of stuff is how we can relate to what's happening. How do we relate the tools we've been given to the problem? How about average acceleration? What is acceleration? Well, we know when we look at this equation that it is the velocity initial across the x-axis. And this is the velocity final across the x-axis. So F always means final for the most part. I means initial in our model. So velocity across the x-axis final minus velocity across the x-axis initial, right? We subtract those two values over time final minus time initial, or delta time. And we can also use this as delta. The change in velocity over the change in time gives us an acceleration. Notice that there is a change in velocity. If the velocity is constant, then the acceleration is what? What value? If I have a constant velocity, what's the acceleration, guys? If we go with this idea. 0. Awesome. Some people are answering. This is awesome. So you're getting it. Because there's nothing. If the velocity final and the velocity initial are equal, right? So the initial velocity was 0, or let's say 10 meters per second, and the final velocity was also 10 meters per second, and we take this equation, 10 minus 10 is 0. Doesn't matter how much time we spend, 0 over some value is still 0. Therefore, the acceleration would be 0. Okay. However, if we use this equation and we said that the final velocity was 20 and the initial velocity was 10, 20 minus 10 is 10. And let's suppose it was over a period of 10 seconds. So 10 over 10 would be 1. So your average acceleration is 1 meters per second squared. And that's what we have here in terms of units, because it's the time step is squared seconds, right? So the way it works is for every meter, we're accelerating per frame. How much are we moving the velocity dial to the right every frame, which means velocity is increasing. So it's going from 10 to 11 to 12 to 13 to 14 to 15 all the way to 20, okay, every second. Instantaneous velocity, then, we can use, calculus to figure this out. A lot of times we can use the limit as time approaches, the change in time approaches 0 for the change in velocity across the x-axis over the change in time. And so we can say delta V over delta T as an example. And we can derive acceleration from velocity. So again, there's a relationship between acceleration and velocity, and from velocity, from position. And so you can really extrapolate, all those values in one acceleration, position, and velocity graph. You can see the difference here. If my velocity starts off small and my acceleration is constant, so I've got a constant acceleration here. And that's something that we're going to be working with for the most part, where we're assuming that the acceleration across a particular axis is constant. It's not a variable acceleration, okay? So acceleration is constant, and you can see that the little vector for velocity starts off from this time step is very small, right? And then it gets larger and larger and larger and larger, and that's what the velocity vector would look like. It continues to increase, or we add the acceleration to the initial vector quantity to get the next value, typically. Again, probably not exactly to scale. So again, what we can do is we can use the instantaneous acceleration graph, and it's the same thing. We can see that the slope of the green line, or a line tangent to the curve, as an example, at that particular point in time, is equal to the instantaneous acceleration, just like we did when it came to velocity. We can map all three things on the same graph, and we can look at different pieces of it. So here in the first graph, we can see a position graph. So this is our position time graph, or displacement time graph, where this is the displacement across the x-axis, and here's the time along the displacement on the x-axis, but it's shown on the y-axis, right? And this is the time across the x-axis. Okay, so we can see that at time A, here we can see that we've moved away from the origin, right, some number of units. And you can see that here it relates to the same thing when it comes to velocity. Velocity goes from 0, right? And we have a displacement. Yay, awesome. And then we have a constant velocity from time A to time B. Almost looks like a straight line graph, right, as an example. But it tapers off, so velocity actually goes down. It kind of curves downwards again, or it doesn't go completely linear here. It's not as linear in this particular time step. And so it goes down, and then it continues to fall as we approach, the apex of the curve here, the position curve, right? And then as it comes downwards, you can see that now what's happening is the displacement is going backwards, so we're actually moving in a negative direction, right? Back towards the origin again, okay? So that's the velocity graph, and at the same time, we can see that when the acceleration is happening. So we have a constant acceleration, right, from here to here, and there's a constant because it goes from 0 to some number, right? It started off at 0, x initial was 0, x final is greater than x initial, therefore there's some kind of acceleration in this example, right? So we can see, but it's a constant acceleration because of the curve of the velocity of the graph is just linear, right? So constant acceleration. However, from here to here, there is no acceleration, so the acceleration is shown as 0, and so on. So really great relationship from one. I think I really like this this graph. It kind of plots all three different properties that we always like to talk about in physics, which is position, velocity, and acceleration. And we would include this in your rigid body component. And if you actually look at the SDL template that I've given you, the SDL engine, it has a rigid body component that includes velocity and acceleration. All right, let's move on. So when an object's velocity and acceleration are in the same direction, the object is speeding up. When an object's velocity and acceleration are in the opposite direction, the object is slowing down, right? And we know that that is the case. We're also going to talk about force eventually, and acceleration. There's a direct kind of relationship between acceleration and force. We can say that if there's no force, therefore we have no acceleration. We're going to talk about Newton's laws as we move forward in this course. And one of the laws, the second law of motion for Newton is F is equal to ma, where m is mass and a is acceleration. If acceleration is 0, and when we multiply, with the mass of the object, then so too is force. Force becomes 0. So there's a direct relationship between force and acceleration. 0 force a lot of times means 0 acceleration, and vice versa. Right. One thing that we always get sometimes is we might think about things as in a negative acceleration. And sometimes when we think about negative acceleration, it doesn't necessarily mean that the object is slowing down, because it's still an acceleration, right? So if the acceleration and velocity are both negative, as an example, then the object is speeding up. It's just going in the negative direction relative to the origin. Okay. Let's continue with this motion diagrams, and this is something that we may make you do on a test or whatever. So let's think about the motion diagrams that we have here. There's 3 different kinds of motions that are described here. So the first one is constant velocity, right? The second one is when the acceleration and the velocity are in the same direction. We can see that the time steps here are closer together, right, as an example. and then they get further apart because as the car continues to accelerate, there's more displacement away from the origin, right? So this is what it would look like. So a smooth acceleration from 0 to whatever maximum speed that this car has achieved. And on the other hand, this is where the acceleration vector is in the opposite direction relative to the car's velocity. So you can see that the velocity vector becomes smaller and smaller, whereas the acceleration vector maintains the same constant size. Again, we're using constant acceleration for these examples. So motion diagrams are really nice because they kind of describe the motion that we're seeing here. So again, constant velocity, you can see that the same size of the vector that we talked about before. Acceleration in this case is 0, right? Acceleration and velocity again across in the same direction. We can see that the cars in the images become further apart as time increases because things are continuously speeding up. And the same thing goes with on the opposite direction, where the velocity and acceleration in opposite directions, the images become closer and closer together as the car continues to slow down gradually, right? So really the diagram, all those diagrams represents the car as the motion of a particle. We don't care about the car's size or what it looks like. In your mind, you should always think about any kind of thing that we're talking about in this course as using the particle model. Okay, these are the meat and bones of what we want you to take away from today, all right, which are the kinematic equations. And by the way, these kinematic equations are only working in one dimension, but they can be extended to work in 2 dimensions or 3 dimensions. Okay, when I say 1 dimension, I mean only across 1 axis, 2 dimensions across 2 axes, and we're going to talk about that in 3 dimensions, obviously in 3 axes. All right, so let's take a look at some of these equations. Okay, so the first one, equation number 1, right? And this is the requirements. When your constraint is you have a constant acceleration across the x-axis, then you can say that the velocity across the x-axis final is equal to the velocity of the x-axis initial plus the acceleration across the x-axis multiplied by time. Okay, so this is the first equation. So one thing this doesn't give us is no information about displacement, okay, as an example. So let's plug in some numbers here, and there's some numbers we can plug in. So an example would be if I say that the initial velocity is 20, right? And, then we add in a negative 9.8 meters per second. Let's suppose this equation is working in one axis, let's say across the y-axis, right, as an example, up and down. So an object is falling. You've dropped an object, and the initial velocity, or you've thrown an object here, the initial velocity is 20 meters per second, and you're subtracting, and 20 normally means in which direction, guys? Up, right? Because it's a positive number. If I was to throw an object in the negative direction, that means down. Remember, up is positive, down is negative. In this coordinate space that we're talking about here, on the computer, 20 positive would be down, right? Because remember, we start off for the most part with SDL. The top left corner of the screen from a coordinate space perspective is 0, 0, the origin. Whereas in a Cartesian graph, the origin is here at the bottom, right? So that's the difference between the kind of a coordinate system on a screen compared to a coordinate system in math. So here we're going up. So we're tossing an object up. We don't care about the mass, straight up. And yet every frame, every time step, it's coming down at 9.8 meters per second, right? And at the end, we can move, when we massage the formula, we want to solve for time, right? As an example. So we move the 20 on this side. Whenever we cross the equal sign, right? The assignment operator, then what ends up happening is the value that we move across to the other side switches signs. So it becomes negative, right? So 20 here becomes negative 20 on the other side of the equal sign. And then now we have everything in negative quantities, right? And then we want to divide, because this is a multiplier, a scalar to time, this value here. we want to multiply both sides by the same value, or divide both sides by the same value. If I divide this side by negative 9.8 and this side by negative 9.8, here negative 9.8 gets canceled out, and here we're left with a negative 20 over a negative 9.8, and because we have a negative over a negative, we can cross out the negative signs so it can be a positive number, so 20 over 9.8, which makes sense because guess why? Time, unless you're a time traveler, can't be negative. And it works out to be 2.041 seconds in this case, given these parameters. Does that make sense? I've just plugged in some values where the initial velocity is positive 20 and the acceleration on the x-axis, or on the y-axis in this case, would be minus 9.8. Let's continue with the second equation. Second equation is for constant acceleration. Okay, so again, both for constant acceleration. Okay, and this one, what we've done is we've massaged the we can figure out the average velocity across one axis, where we say add the two things up. We say the initial velocity plus the final velocity, divide that by 2, and we have the average velocity across one axis. Okay. So again, this applies only in situations where the acceleration is constant, and it doesn't tell us anything else about other factors. There's no time involved here, so if you don't have a time value, then what happens at 2 seconds? Is that what you said, Miguel? Well, there is no time factor here, so we don't know anything about 2 seconds. All we know is the initial velocity and the final velocity over 2. 2 is it doesn't matter if we had multiple velocities and we add them all together, then we can add them and average them together. So if we're going back to this as an example, what happens at 2 seconds, right? Well, in 2 seconds, what occurs, right? If you start off the final velocity, this is the final velocity, right? So the final velocity, if we assume that the final velocity, right, is 0 in this previous equation, and the initial velocity is 20. So if the final velocity is 0, guess what that means? Velocity is a displacement, which means when it comes back to the origin where it hits the ground, right, it takes 2 seconds, 2.041 seconds for the object to go up and then come back down. Yeah. When it's at rest. All right, let's continue. So that's kinematic equation number 2. Kinematic equation number 3, all right? And this is, again, for constant acceleration only, all right? And so this equation, we use this one where we have time. So it starts off, we derive it from this. We have x final is equal to x initial times the average velocity over multiplied by time. That's the original equation. And that comes from this equation, the first equation right here, right? And, as an example, very similar to that. Well, here what we're doing is we're massaging the equation to say something like, time is equal to x1, as an example, or x final is equal to x initial plus 1/2 of, and we've split up velocity initial across one axis plus velocity final multiplied by time. So this is another way of doing it. And this gives you the position of the particle in terms of time and velocities, but it doesn't give you anything to do with acceleration. So acceleration has been removed. So we don't have acceleration, but we have velocities. We can use this equation. We must have time too. So time and velocity. It's reaching the ground. When it hits the ground, Giuliano, and there's no motion, there's no more displacement, velocity is 0. All right, so let's continue. So kinematic equation number 4, again, for constant acceleration. Here we've massaged the equation, and this is a key equation, guys. Truly a key equation. Why? Because when we think about this equation can be extended, and it's kind of the equation that we use for a parabolic motion, right? If we were to extend this not just in one direction, but in 2 directions. Again, this would be x final is equal to x initial plus Vx initial t plus 1/2 of ax t squared. And if you were to extend this, it'd be, and if we looked at position final, so let's extend it for 2 seconds, and we're going to talk about this again next week. Position final is equal to position initial plus, P final is equal to P naught. Sometimes we call it P naught or P initial, right? Plus Vt plus 1/2 at squared, where V has both components of x and y, okay? So we can extend it, and once we do this, we have parabolic motion, and this describes a great quantity of anything that we toss. So for example, for your Wookiee equation, it's going to be derived in some sense from this one, okay? Because this we have some kind of grenade. If you're tossing a grenade, you're going to use this equation for the most part, right? Because it's going to be described in parabolic motion, where ax is the acceleration due to gravity, okay? One thing it doesn't tell you is the final velocity. We don't know what the final velocity would be in this particular equation. And a lot of times, I've also pinned this one up here as well. And you guys should recognize it if you remember algebra. This is the algebraic equation, if you will. And what it does is it just says, if I want to isolate x as an example, I want to isolate x, then what I need to do is I need to, based on the quadratic equation, the quadratic formula, ax squared plus bx plus c is equal to 0, right? Where you have your, there's 3 different terms here, right? And so too, this is written in reverse order. Think about this, right? You have a squared term, you have a linear term, and you have some kind of term that you're adding, ax squared plus bx plus c. If I'm going to isolate time, then time would be the x in this kind of equation, right? So if I want to know the time it takes for an object, as an example, there a lot of times are 2 solutions, right? And what we want always is the positive solution, right? And why? Because if we will get a negative potential solution, another place where the parabola will cross, the x-axis, the origin, right? As an example. And all we care about is positive time values. We don't care about negative time values because we're not a time traveler, like I said before. So if that's the case, let's suppose if we sub in some of these values, say that the final position, if we assume that the final position is 0, and we're throwing an object, we're kind of describing an object that's being thrown, where the initial, initial position is 50, so that means 50 away from the x-axis, 50 away from the origin, right? Final position is 0, okay? And then we can say that if the velocity across the x-axis initial is negative 20, right? And the acceleration across the x-axis is negative 4.9, we've obviously it was actually negative, a 9.8 divided by 2, which is negative 4.9. And if I ask you to solve for t, how do you do this, right? Well, you use the quadratic formula and you sub stuff in. You say that you take a negative b, this would be the b in the formula because this is the bx. So this is the linear term, right? This is the squared term here, right? So the squared term is a, and if I was going to mark this, you're gonna see that there's value in using the quadratic equation here. Let's do things in reverse order. So I'm just going to grab this one. I'm just using some values to sub in here so you can see them, right? So when we write it in reverse order, it looks like this, right? So plus, right, 1/2 of at squared. That's what it looks like, or 1/2 at squared. Here, 1/2 of at, we can say that this is ax squared, right? That's this part. Doesn't matter what we put in the a, 1/2 of 9.8, 4.9. We don't care about that. This is the a term, right? Here, this would be the b term, right? So bt. And this would be the c term. So we take the values of c, b, and a and plug them into the quadratic formula. And once we do that, we can start solving for t. We want to move some values on this side, right? And the way to do this, and to do it because of the squared nature of the function, the quadratic formula, we're going to have two solutions. We're going to use this formula, and so we plug them in. So we say something like, okay, so minus b, so minus 20 is 20, plus the square root of, and the square root is going to stretch all the way here, not just over here, right? The square root of 400, so b squared. So if I take b, right, squared, negative 20 times the negative 20 is a positive 400, minus 4ac, all over 2a, right? Where a is negative 4.9 and 2a is negative 9.8, right? Back to what it was before. Then we solve for this. We solve the equation by working out the values that we get from here, and we're going to get 2 time values, right? Because we have a negative b, and we have this other symbol here, which is plus or minus. We could get another value. We're going to calculate both the plus and the minus. It's either one or the other, and only one of them is going to give us a positive time value, okay? Only one of them is going to give us a positive time value. Because again, you have 2 possibilities, either plus or minus, because it crosses a parabola across the x-axis twice. Okay, so that is a way of thinking about it. It's like these equations were made for each other. Absolutely. Let's continue. We have a lot more to cover. All right, equation number 5, right? For constant acceleration again, where, v squared final is equal to v squared initial across the x-axis plus 2ax, right, multiplied by x final minus x initial, which is really the displacement formula, x final minus x initial, right? And this gives us the final velocity, right, in terms of acceleration, but it doesn't give us anything around time. So if we don't have time, but we have acceleration, initial, and final velocities, we can figure out the final velocity based on that without time being involved at all. And I think this is, again, all these equations are going to help us solve different problems based on the information we've been given in the problem statement, okay? Let's continue. How about when acceleration is 0? Well, we know when acceleration is 0, we can simplify certain equations. We know then if velocity x final is equal to velocity initial, then all we want to look at is velocity x. We don't care about, and there's no acceleration. Whatever the velocity is what it's going to be. There's no acceleration at all. So we can sub out vxat and just put in vxt. So this is where x final is equal to x initial plus vxt under constant acceleration. So this is the kinematic equation summary. If you're going to look at one page, page 48 is giving you all the different kinematic equations for the most part, and there's a couple of other, there's another variation up there as well that gives you everything you need to start thinking about how do I break down a problem given the information presented in the problem. Some problems will give you more information than other problems. Okay. We've taken a graphical look at motion before, but we're going to get another one. We can see that the slope of the line is a slope that's tangent to the curve, right? And if we notice that the slope changes, we know in this particular case, if velocity is on a slope, that the velocity is changing. If velocity was a linear line, velocity is constant, therefore there's no acceleration. Okay? Constant acceleration, right, is what we're looking at, and you can relate velocity and time. The velocity time graph outputs acceleration. And when we have a 0 slope, there is it indicates a constant acceleration when the slope is linear like this, but parallel to the time graph. Okay. Let's talk about my favorite friend, Galileo Galilei, right? I think he was killed as a heretic, back in the the early or the mid 1600s, right? He was an Italian physicist and astronomer, right? He formulated these first laws of motions, and he talked about objects in free fall more than anything else. And actually, he was, I would say, a precursor to Newton. All right, so remember, a lot of scientists and philosophers, they kind of built their knowledge on other people, right? So the reason why he was branded as a heretic is because, right, at the end of the day, he was talking about a different way that he described motion. We'll talk about that later on if we have time. So he talks about three types of motion when it comes to free falling objects. One of them is dropped. So if I take an object and I drop it from rest and it goes just straight down, right? The other one is thrown downward, and the other one is thrown upward. And we've kind of described that in an earlier example, kind of up there, in previous slides. So when we think about acceleration of a free-falling object, what do we know about it? We know that the magnitude of the free fall acceleration is always going to be a positive 9.8 meters per second. Again, if it's in the negative direction, going down, we might apply a minus sign here, okay? Gravity decreases, as an example, with increasing altitude. That's also what we know, right? So the higher up an object is, the further away from the center of the Earth, right? As an example, the pull of gravity, the gravitational constant of the universe, right, basically states that the farther an object is away from the origin mass, right, that is attracting it, the lower the intensity of the gravitational pull, right? So the farther up an object is from an altitude perspective on top of the Earth, then it's going to be less gravity, right, for the most part. And gravity varies with latitude, and that's what we know as well. For our examples, we're always going to think about constant acceleration, constant gravity. We're not going to, consider cases where gravity is changing. We're always going to think about gravity as a constant acceleration because it makes it easy for us. And for most cases, for games, it makes the most sense. I see a hand up from Miguel. And Miguel, is that a previous question? Maybe I didn't notice it before. Is that a question you have? Miguel? Yeah, I see your hand. You have a question? No. Okay, let's move on. So one thing that we're going to do in our course is neglect air resistance. We're not going to care about air resistance for this course, okay? And we're also going to, it's free fall then is an accelerated motion in one direction, okay? And we can use the model of a particle under constant acceleration for this. And we can also see that we can let upward motion be positive and downward motion be negative. And this way, what we would say is acceleration across the y-axis, if that's the only axis we're using, is a negative g, which is a negative 9.8 meters per second squared. And note, displacement is in the vertical direction when it comes to motion. Remember, motion in one direction doesn't matter if you're on the x-axis or on the y-axis, but all you care about is a single axis, which is important. Neil's asking, will we do air resistance next semester? No. I'm not sure if air resistance is going to be something you're going to be dealing with, Neil, necessarily, although we can talk about air resistance when we think about when we think about motion in two directions, and there may be a question I've given you that says that gives you the results of wind as an example, but not necessarily air resistance. We could think about air resistance as a force, right, as an example, but right now we're not talking about forces. We're only talking about motions and kinematic motions in one direction. All right, so free fall, an object is dropped. So we see an object, it's kind of going down. As an example, we can say that the V initial, or V naught, sometimes also called V naught, is 0. We start off, we hold an object, and then we let it go. And then the acceleration is a negative g because it's going down, just falling down straight, okay, as an example. And again, let up be positive, and let's use the kinematic equations as it falls, right? We can say that, we're thinking about it as gt, right? Because our initial velocity is 0, as an example, and that's what's happening. If we have a thrown object, that's a different scenario where the initial velocity cannot be 0. We're actually imparting energy, or we're throwing an object down, as an example, and we're giving it an initial velocity, and it cannot be 0 when the object is thrown downward. The other case, this is the third case, is where the object is thrown upwards, right? And it's but the velocity is in one direction, and the acceleration is in the other direction, right? So this is where it's going to slow down as the velocity keeps on being chipped away by acceleration. It's going to keep on slowing until it gets to this point right here. Then the velocity is going to go in the negative direction, right? As it continues to accelerate, and it's going to go faster and faster and faster until it reaches the point where we threw it in the first place. Okay? So that's how it works. So again, velocity is in the upward direction, so it's positive. But again, gravity is in the negative direction, so it's negative. The acceleration is negative. Okay. So one thing to note is when we throw an object upward, the motion is symmetrical. All right. So in other words, the time up is usually the time down. And then therefore, when it reaches the place where we threw it up in the first place, V positive, when it comes back down to our hand, is equal to V negative when it comes to that point where we threw it up. So if I throw an object up in the air, example here, let's say, for example, I'm standing on the ground and I throw an object up. If I threw it up with 10 meters per second velocity, it comes down. When it comes down to my hand again, it's at negative 10 meters per second. It's symmetrical motion. Okay, that's something that he observed, Galileo. So here's the problem, right? So we have, this is a typical problem that you'll see. And again, you'll see stuff on the test that is eerily similar to this problem, okay? And when I say eerily similar, I know that Josh is going to laugh at me, but that is something that we were always told when we were learning physics. And basically, acceleration is upwards, and acceleration, A, at the point A is upwards, okay, is up, okay? The man in this particular case, you see an object or a person, let's just put a person, he's at the top of a 50-meter building, right, as an example, and they are throwing up an object in the air, and you can see that the velocity across the y-axis when we start off at position A is 20 meters per second, okay? The acceleration across the y-axis, again, all on a single axis, is negative 9.8 meters per second. So the instant that the object is thrown, negative acceleration is already being applied to it, okay? And it reaches the apex, which is position B at some point here, and you can see that it's taken 2 seconds, 2.04 seconds for it to stop, for the velocity to be 0. So we can use that equation we used last time. When the velocity reaches 0, when it hits the apex, right, that took us 2 seconds to get here, 2.04 seconds, right, when the velocity stopped. And then on the way back down, when it comes down to here, another 2.04 seconds for a total of 4.08 seconds. Again, a symmetrical motion, 2 seconds up, 2 seconds down, right? Again, where the y, the position on the y-axis is still 0, it's the origin. And then here at this particular instant in time, we have the velocity downwards, or the velocity across the y-axis is a negative 20. So it's symmetrical to the velocity we threw up the ball or the object with in the first place, right? The acceleration is still constant at negative 9.8 meters per second. And then we can let it drop further down from the origin. So now we're in a negative direction. And we can see that in 5 seconds, as an example, an additional, 0.92 seconds, not less, just less than a second, it's fallen to this position here. And at 5.83 seconds, approximately, due to the size, the height of the building, it's hit the ground. Okay, and we can say that it hit the ground with a velocity, a downward velocity of negative 37.1 meters per second. But the final velocity that it's going to have down in here as well is going to be 0, because it's not going to penetrate the ground and keep going. Okay. So things that we know from looking at this diagram, is that the displacement is negative 50 meters, right? Because we can see that it started off at 0, it went up 20 meters, it came down back to 0, and then it came all the way down negative 50 meters to the ground. So that's why we know the displacement is negative 50 meters away from the origin. Okay, where up is positive away from the origin and down is negative displacement away from the origin. Okay, so this scenario, this free fall example, is kind of a basis for some of the problems you're going to get. So displacement equals really to the area under the velocity time curve. And we're going to talk about if we're going to try and solve the total area under the curve, there's some structures we could use to do that. If we were to take this curve as an example and make smaller and smaller rectangles, so divide the curve into smaller and smaller little rectangles to get closer and closer. Miguel says, is this calculus? It is. But we're describing here, we're going to integrate all of the little rectangles together to get a very close approximation about the area under the curve. We're going to add all those rectangles up together. And when we add all the rectangles up, we get an approximate area under the curve. The smaller the rectangles, right? So they're very much smaller, thinner sliced. The thinner slices we take, the closer and closer we get to the actual area under the curve. And we can estimate the actual area by using the limit as time approaches 0. And again, for the sum of all n's, where the velocity across the x-axis initial multiplied by the change in time, n, where you can sub in n as time, as an example, is equal to the integral of the time initial to the time final for all velocities across the x-axis multiplied by time, and then dt, which is delta time. So this integration formula, we can actually figure out the exact, or very close to the exact area under the curve for any curve, right? Whether it's velocity time graph or acceleration time graph, it doesn't really matter. And this is something called the definite integral. That's how we would do it. Again, we're not talking about calculus, but I wanted to describe a method that we can use to figure out the area under the curve. And again, displacement equals to the entire area under the curve. So again, I'm going to show calculus, but I'm not going to do calculus. And we're just going to skip this slide, but I've put it in here for your reference, where acceleration across the x-axis is equal to delta v across the x-axis over delta t. And what you can do is you can derive acceleration from velocity. That's what this is basically saying. And you can go back the other way, where if you want to find the velocity from the acceleration, you can just take the integral from time 0 to time t, right, for all accelerations across the x-axis. All right. And what that does is when we use accelerations, when we use the kinematic equation and we get them from integration, we use calculus to derive them. This is where we got the formulas in the first place. Then what we can do is we can derive the formulas from the values that we have, starting off with a very simple formula like this, where velocity final across the x-axis minus velocity final initial across the x-axis is equal to axt. And we know this from some of the formulas that we were working with before. Again, it's just another representation of the same thing. All right, so that covers kinematic formulas And it also covers, and those kinematic formulas are the ones that you need to know and practice for your midterm test, okay? So here are some steps in general problem-solving approach that we use when we look at complex problems or problems that are worded to us. We're given a word-based problem, a word problem, and we're going to figure out, how to solve that problem with math, all right, and physics. So one is we conceptualize. In the conceptualize phase, what we want to try and do is break a problem down and draw it out. We want to categorize the problem. What type of problem is this? Is what we're asking when we categorize. Is it is acceleration, constant? Is velocity constant? What's the time value? What are the properties? And we analyze, in the analyze phase, we analyze what attributes have been given values, all right? Neil's asking, is it open book? Can we look at our practice code? Absolutely, you can do all that stuff. It's always open book and you get 2 attempts or multiple attempts. For our purposes, is the velocity of the angle converted to a vector and then normalize? Yes, and you can use coding to solve your problems as well. But for the stuff that I'm talking about when it comes to strict formulaic, formula kind of stuff, applying a formula to a problem, then you'd have to use the formula that I've given you for kinematic equations. But yes, for your purposes like game dev, you're right. So again, when we conceptualize, we think about the situation, try to understand it. We gather numerical information and try and put them in the places that we know about. And we start thinking about how to draw it out. We simplify the problem. Can we ignore air resistance? Can we use objects as particles? Yes, we can. We can classify the problem, and we can use substitution to substitute numbers in there as opposed to x's and y's and all that kind of stuff, which is important to do. And then we want to select the relevant equations to apply to the problem in order for us to solve. For example, if we don't have time, we use one equation. If we don't have acceleration, we use another equation. If we don't have velocity, we use a third equation as an example. Okay. Typically, we have acceleration all the time. And then we finalize by, using the equation and solving the problem. One thing that we can do sometimes is break a bigger problem into smaller sub-problems, solve individual problems or the sub-problems first, then combine the results later into the final results. Sometimes we have to do that as well. Okay, and actually this is the step that we take most of the time when we want to solve complex issues in general, right? We take an issue, break it down into chunks, solve each chunk separately, and then put all the answers together to get the final solution. All right, from here on in, this is some of your homework, and I've given you some examples here of how to look at this stuff. So here's problem example 1. Again, the examples that I've given you are going to be eerily similar to the examples you might get or the questions you might get on a test relevant to, or related to motion in one direction. So here's one. A racing car starts from rest at time 0, right, and reaches the final speed v at time t. If the acceleration of the car is constant during this time, which of the following statements is true? A, the car travels a distance of vt. True or false? The acceleration is constant, right? Then do we care about it, right? Think about this for a second. The next one is B, the average speed of the car is v over 2. Is that true? Right? And the magnitude of the acceleration of the car is v over t. Magnitude of the acceleration of the car, v over t. So think about these questions and how would you answer them? Where would you go to look for these kinds of things? And they're thinking questions as opposed to, writing questions with formulas. And then the other one is none of the statements are true. A through D is true, right? Okay. So let's move on. Problem examples 1 solution. The initial velocity of the car is v naught, where v naught is equal to 0, and the velocity at the time t is v, right, as an example. So, yes, they're on YouTube. The constant acceleration is therefore given by acceleration is equal to delta v over delta t, where v final minus v initial over t minus 0, where we start always at 0 for time. Time usually starts at 0. It doesn't start at 1, or typically, unless you're told that at time 1 to time 5, or time 3 to time 10, that interval of time frame. But normally we start at 0, right? So we can say that it's just t at the bottom, where v minus 0 is just vt. So acceleration is equal to v over t. And the average velocity of the car is the velocity vector, which is the velocity final plus the velocity initial over 2, right? Where the velocity final plus 0, because the initial velocity started off at 0, over 2 is just the velocity over 2, all right? So, and then the final thing is the distance traveled in time, t, is the change in x, which is equal to the velocity vector times time, which is vt over 2. And a special case where acceleration is 0, and hence where velocity final is equal to velocity initial, then we can say that v is 0. We see the statements A, B, C, and D are all correct. However, in the general case where acceleration is not equal to 0, and hence velocity, the final velocity, is not equal to 0, then only statements B and C are true. And statement E is not true in either case, where statement E is none of the statements. Okay. Problem example number 2, a little bit more numbers here, okay? The position versus time for a certain particle moving along the x-axis is shown in figure P2.1, okay? Find the average velocity in the time intervals A, 0 to 2 seconds, B, 0 to 4 seconds, C, 2 to 4 seconds, and so on. Let's think about this for a second. Okay, so we're asked for the average velocity in the time intervals. How do we find the average velocity? V final plus V initial divided by 2, right? Typically, right? We could do that. But it's given for a certain group of seconds as well. We've been given the number of seconds, 2 seconds, 3 seconds, all that kind of stuff. So which kinematic formula can we use to solve this problem, right? Well, let's take a look at the solution. So we know that where x is equal to 0 at time t is equal to 0, and x is equal to 10 meters, right, at time is equal to 2 seconds, then we can say that delta x over delta t is the Vx average. That's the formula we would need to use, right? So we can say that 10 meters minus 0, 10 minus 0, is, and then 2 seconds minus 0, the initial kind of seconds, is equal to 10 over 2. And notice what you're left with is meters per second. So it's 10 divided by 2, 5 meters per second is the average for A between 0 and 2 seconds. Could you figure this out with by using the graphical approach? So in other words, if I said from 0 to 2 seconds, we went from 0 to 10 meters, right? Then the displacement is 10 meters over 2 seconds. 10 meters over 2 seconds, we can get an average speed of 5 meters per second. Okay? Let's see if we can do the same thing for this time slice from 0 to 4 seconds. Okay, now this is different. So here's the initial position. Here's the final position. Remember, all we care about is the displacement. So if we say that the final position is 5 meters and the initial position is 0 meters, and the initial time is 0 meters, and the final time is 4 seconds, so 0 seconds and 4 seconds, we can say that this is 5 over 4, right? In terms of total average velocity. Let's see if I'm right. So again, you can see that 5 over 4 is 1.2 meters per second. We can actually look at the graph and try and figure it out. We really don't care about the up and down. We care about the final displacement, right, from the origin. Okay, let's do it from the next part, from 2 seconds to 4 seconds. 2 seconds, the initial displacement is 10. 4 seconds, the final displacement is 5. So 10 minus 5 is a negative 5. It's going in the negative direction, right? And 2, so 4 minus 2 is 2, right? So when we're going in the negative direction, it's negative 5 over 2, right? Which is negative 2.5 meters per second. Let's see if I'm right, right? Negative 2.5 meters per second. And so on. Okay, so this is kind of an easy way of thinking about this. And we're using, once we figure out the formula to use, we can figure out the rest. Next, another problem, okay? A person walks first at a constant speed of 5 meters per second along a straight line from point A to point B, and then back along the same line from point B to point A at a constant speed of 3 meters per second, right? What is her average speed over the entire trip? Okay, and what is her average velocity over the entire trip? Okay, so one thing to note is what it says here, speed is positive whenever motion occurs, so the average speed must be positive, right? Because we're looking for average speed, not average velocity, right? For the velocity, we take up as positive for motion to the right and negative for motion to the left. So its average value can be positive, negative, or 0. Okay, that's the velocity. But we really care about the average speed here. So remember, speed is distance over time, right? And that's what we care about. And this is how we figure this out. Problem 3, solution. We sub in the values that we've been given. And so the average speed is 2, or d plus d, and so on. I'm not going to go through this. I'd like you to read it, again, because I want to talk about other things that are maybe less obvious, right? And then we sub in the values. Here are some example problems that are left for you. There's 3 left for you that have no solution that I'd like you to do, for yourself. Try and see if you can figure this out. What solutions would you use? Okay, how would you approach this problem? Okay, and then we'll end for the day. A particle moves according to the equation x is equal to 10t squared. Desmos. Map it out, guys. That's the first thing that I would do. Where x is in meters, right, and t is in seconds. So the displacement is in meters and time is in seconds. Find the average velocity for the time interval from 2 seconds to 3 seconds. Again, most important thing is map it out. So what I would do first is, let's see if I can use Desmos, right? And if we can use Desmos for a second to plug in the solution, 10t squared, what does that look like? So we would use, 10t squared, right? We can add a slider for t, right? Where t is a bunch of values, right? So we can see that that is a slider, right? And it gives us the values relative, as an example to t, and we get answers. So if I say where t is negative, or we always want to go where t is positive, obviously, because positive t, you can see that it's exponential. We can change the t value so we can map it to an x, and we see a graph that looks like this, all right? So first thing for me, what I would do is graph it out. This is what the value looks like, okay? Where x is t, we don't care about values that are negative, right? Again, where, 0 is less than x, or x is greater than 0 is what I want to say, right? That's the most important thing. We don't care about values, let's see if I can do this again, where x is greater than 0. We don't care about values where x is negative, because x represents t, which is time, right? So we can see that each value here represented in this graph is values of time, right? And we've been given some instructions. We say that between 2 seconds and 3 seconds, okay? So that's over here. So between 2 seconds, you can kind of zoom out a little bit, okay? And we can actually try and, put it together. Here's about 2 seconds. So at 2 seconds, right, the displacement is 40, right? And at 3 seconds, that's this line right here. It's going to go all the way to 3 seconds, right? And again, you can also change your scale. Let's make sure that I get to the right position. At 3 seconds, it's 90, right? So 90 minus 40 is 50. So that's the displacement difference between, and you're only talking about 2 to 3 seconds, which is 1 second, which is 50 over 1. So it's 50 meters per second, right? That's what I'm estimating just by looking at the graph. Maybe I'm wrong, but that's what it looks like. So from 2 to 3 seconds. Okay, now find the average velocity from the time interval from 2 seconds to 2.1 seconds, and you plot that in. You use the same formula and you plot this in. But really, at the end of the day, you want to plot your graph, and you can put whatever time intervals you want and whatever scale you like to describe what you're doing. Okay, this one. Find the instantaneous velocity of the particle described in figure P.2 at the following times. T is equal to 1 second. What's the instantaneous velocity? How do you find the instantaneous velocity? What formula do you use for that? Okay, and the next one is, and here's the more difficult one, or maybe not so difficult. Draw motion diagrams. Motion diagrams are fairly straightforward. For an object moving to the right at a constant speed, for an object moving to the right at speeding up at a constant rate, and so on. Draw motion diagrams. And the reason why drawing motion diagrams is really cool is because it gives you a sense of motion, how things accelerate and decelerate. Actually, coming back to our discussion, and I'll end the day here with this kind of these kind of thoughts for everyone here. Remember what we did with AI. When we did things like, arrival, right? When we did seek behavior, steering behavior with AI, for those people who were in AI, and maybe there's some people here that didn't take AI for whatever reason, or took it, or are going to take it in the wrong order or whatever. When we did AI and we decelerated towards the arrival position, right? You can see what we saw was we had the object or the particle coming, between time intervals became closer and closer together, right? And that idea is something that would have been, if we had known about physics at that particular time, I think it would have made the concept of deceleration a little easier. Okay. By the way, do I think physics is easier than AI? Yes, maybe in this case, from a programming perspective, I think it would be easier in some ways. But if we didn't have AI in your second semester, then you couldn't really add something like an AI into your game, and therefore the game would be maybe a little bit less interesting. Lim is the limit. That's what it is. The limit as x approaches 0 usually, where x is time, or t approaches 0. Yeah, Sam, you're right. I mean, I think we can get pretty high level. I think you need both of them. You know what I'm saying? At the end of this semester, I think you'll have most of the things you need to start thinking about building a physics engine. You're going to have another physics class after this one. I'm not sure if it's going to be next semester or the semester after. But at the end, the idea is you'll know about basic motion. So if you want to make a platformer now, after this course, you'll know a lot more about how it should work. How about tossing a grenade? How about all these things? Could you have looked it up previously in other semesters? Absolutely. But I think you're going to get the basics from us this semester, and it'll give you some good practice on how to do it with your SDL template. All right, so that's it. Let's talk a little bit of administration before we leave. So a couple of administrative issues. One, I have set up a series of groups on up on Blackboard. So please, 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 you must subscribe to one of the groups in order for you to do the assignment. If you don't subscribe or register for one of the groups right here, and I've made 20 of them, right, with you and your partners as an example, and I can make more if I need to. As an example, right now I only have 20, so if they're all full at the end, and you want more groups because you would like to work more alone than not, I will create more of them. But what I'd like you to do is try and partner with people, because there are several parts of this assignment. One of them is the theoretical part, and the other part is the programming part. And I think if you can have at least two partners doing each of those things, one partner doing one partner to the other. The third partner obviously would benefit from doing something extra, or making the assignment more interesting. But at the end of the day, I recommend two, but I would allow three. So Neil says, should be under assignments. I don't see anything. If you don't see anything under assignments, because again, if we look at student preview, let's take a look at student preview for a second. What you want to go to tools, right? And then you go to groups. So that's what you should be seeing right now. Okay. Tools, groups. Okay. So please sign up if you haven't done it already for a group. All right. Again, groups of one are okay. If you need more groups, I will make them. You gotta let me know if they're full. I will continue to create more groups, but I recommend two people for this assignment. And I would accept three if the third person is going to do something for you. If the third person is a ride along and if they don't talk at all, they don't do anything for you. I mean, remember, I'm gonna meter what you guys are doing with your assignment. So if you say something like, "I got nothing. I'm just riding along. My name's Tom, and I'm just a rider," right? Then you're gonna get zero, right? So so please make sure that if you pick a partner or partners, there's things that everyone's going to do. Okay, because I'm going to look at those things. Any questions around assignment 1 and group forming for assignment 1? I will have different groups for each assignment, just like I've done in the past for AI. And so this way, if you don't like your partner, you don't have to stick with them in the second assignment, in the third assignment, or the fourth assignment. You can't see assignment 1 unless you join a group. Okay, so you need to join a group before you see assignment 1. All right, so then you go to assignments. So if you go to assignments on the left, and if you've joined a group, then if you notice, only group members can see the assignment. The assignment should be tagged inside of here. Let's take a look, make sure it is, unless I made a mistake, and I did. Thank you for that, Herman. Just put that in there. So let's take that assignments and toss it in there. That should be in there. And I do apologize for that. There we go. Awesome. Thank you for that. Okay, any other questions around this? So yeah, so I think that, what I'd recommend is start on your assignment as soon as possible. I see is that a hand? Miguel? Yeah. Do you have more physics exercise to practice all the formulas? Yeah, we're going to get more of them as we go, for sure. And during lab, Joss may give you additional physics problems to help you study for the test, as well as help you with the assignment. Ethan, the starting framework is the same starting framework you use for AI. It is the SDL framework. And so again, one thing that we've been using, see if I can, external links. I haven't put it in. Okay, let's add it here. So I'm gonna make it so I'll call it assignment resources. I'll make a new section for this. So let's do that. So we'll say, kind of add a new content area, and I'm going to call it assignment resources. And under assignment resources, we'll put the link for the framework, which you should already have from last semester, but you may not, or you forgot it, or you weren't part of last semester. So where it is, if you go to github.com, George Brown College, this SDL engine stuff is what we're going to be using. And I know that Joss is going to go over using the SDL engine to some degree, some detail. Okay, so that's the assignment framework download, and I put it in inside of assignment resources, and you should be able to see that now. Can you? Why is that gone? Where did I put it? Under assignments? It was there for a second and then gone. Oh, I put it here. Let's move this to assignment resources. Excellent. So there, assignment resources now has the assignment framework download. Other question from Gabriel. Are we still learning STL stuff because it should help us get better at C++ and using Unreal? Well, you're learning a bit of whatever you need, Gabriel, to be successful at your lab and your assignments. But I don't believe Joss is going to do more of a tour of the STL framework. I'm definitely not going to do that. I'm covering theory on my side. So it's going to be Joss. If you have questions around the STL framework and you don't know how to do something, then Joss will be your man. And is it the same as we're using in the labs? Yeah, whatever Josh shares with you in the labs, Miguel, is the same framework that I'm using here. I've just put it up here for you again. You don't have the assignment resources tab. Let's see if you do. Hold on a second. So enter student view. Yeah, you do. You should see it right now. Assignment resources. Try again. Refresh, Neil. Let's see if you have it now. And you should. Okay, any other questions before we go? Still don't see it, really. How about anyone else? Does anyone else see assignment resources? You should see that. It should be available to you. Okay. Samuel doesn't see it. It should be available to you across all sections. I'm not sure why some of you see it and some of you don't. Let's just also put the link inside of here. Why not? I'll say build. We'll do another web link and we'll say something like, okay, let's do this. And we'll say assignment framework download. We'll put it in there too. All right, so it's also in your assignments area. Okay. Just in case it's the same thing. All right. Awesome. So again, it's the same framework that we've been using the entire time. There's nothing different about it. It's the STL engine that we've been using from AI, and it should be fairly straightforward for you guys to use. Again, I'm not asking for you to do a lot with it because a lot of the stuff that I've asked you to do, there's formulas, there's drawing, and everything else you need to do. It's all, there's a lot of capability that's built into the engine already. So, I mean, it's really you demonstrating how to show your solution from your assignment with code. Okay, guys, good luck on your assignment number 1. Again, it's due 2 weeks from now on Friday. Again, please use the lab as a chance to practice and so on. Guys, take care and see you guys next week. Thank you.